This video is about k-nearest neighbours. This operator implements a k-nearest neighbour model that can be used to classify examples containing both nominal or numeric attributes. The algorithm itself is very straightforward. It simply stores all the details of the training data and uses this to determine the closest example when presented with test data. So we'll cover various parameters. The k parameter, the weighted vote parameter. We'll look very briefly at the measure types, and we'll conclude with strengths and weaknesses of the algorithm. Start with the process. So I have a very simple process. Here's the k nearest neighbours operator. It is taking some data, and in this case the data is simply a sum of the 5 attributes that have been created randomly. In addition, I'm generating the same shaped data using sum, but this data will be different unless I decide to use local random seed so that the data starts out in exactly the same way. So what happens is this training data gets sent to the k nearest neighbours operator, the test data gets sent to the apply model, where the model from the kNN is applied, and then we'll just look at the performance just to get a sense of how well it's doing. Firstly, let's look at the parameters to the kNN operator. So k is 1. You can set this to anything obviously, but 1, we'll start with 1. This is the number of nearest neighbours used by the algorithm to determine which of the training examples should be returned. So obviously when k is 1, it will find the nearest. If you set this to another thing like 2, 3, whatever, then the algorithm will find the average. So in this case of a regression, i.e. a numerical result, it will perform some sort of average to return the regression result based on the k nearest neighbours. For a classification, or where a nominal value is being returned, then it will, I believe it will use a voting approach and choose the most common to return. You'll notice there's the weighted vote parameter. Now I've played with this, I can't get it to do very much, so I just ignore it frankly and leave it. It says in the help that this modifies the behaviour of the algorithm by using similarity weighting. Well, I've never made it really work in a way I understand, so I just ignore it. Next one's measure types and mixed measures and so on. The most important parameter is the measure types, and there are a big variety of these. You can choose from mixed measures, which lets you mix nominal and numeric values. Nominals, where you can choose from a large array of nominal similarity measures. Numerical ones, where you can choose from a similarly large array of numerical distance measures, and Bregman divergences, whatever they are. I have no idea. I leave them alone. Anyway, far too much detail to go into any detail at all, so I shall just pick mixed measures for now. So how does mixed measures work? How do mixed Euclidean distance work when you have nominal and numeric attributes? Basically, for nominals, a Euclidean-like distance is used where each possible nominal value is taken to be orthogonal to the others, and it has a unit length. So what that means is, if you have two examples where the first attribute is fruit and the value is apple for one and banana for the second, then the similarity between these is 0, they're not the same, and the distance is taken to be 1 for that attribute. If there's then a second attribute, sort of colour, and that has the value green for both attributes, then the similarity is 1 for that and the distance is 0 for that attribute. For the examples as a whole, the distance is the sum of the squares square rooted. So it's 1 for that first example. Apple, banana, green and green would be a distance 1. If you had a third type of fruit, such as grape, that would have a distance 1 from both apple and banana. Anyway, by this method you can build up a nominal distance based on a Euclidean-like measure. Important point though, it's important to realise if you do mix nominal and numerical attributes, it's important to normalise the numerical attributes because they will not be comparable to the assumed unit length of the nominals. A very important point that the k-nearest neighbour algorithm is extremely sensitive to normalising, so get that right, otherwise you'll pay the price. Anyway, so let's run this with k equals 1 and we'll examine the data before we do that. So here's the data, 5 attributes, a label which I think is the sum of those 500 examples. I run it to the end. What we will see is this is the 100 example input training data. This is the test data with a prediction and a performance vector, and we're seeing no error. Why is that? Goodness me. And the simple reason is we've chosen k is 1 and I've arranged by choosing the local random seeds to be this numbers 192 for this and for this, for both the training and test data. The training and test data are the same. So the k-nearest neighbours has basically regurgitated what it knew about the training data, and whenever it sees a test example, it always matches something it's seen before. It will be therefore perfect recall. So therefore the performance is 100% or 0 error. Okay. If I change that to 2, well, it'll do a different job. So now, if we look here, this is the prediction, and I can plot prediction along here against label, and you can see there's a correlation between them, and the performance here shows, yes, it's got 3. The range of the data is from memory 10, 20 or so it's not doing too badly. But this makes the general point that if you set kNN to have k is 1, then it will overfit badly if it sees any training data as test data. That can be overridden to a certain extent by setting k to something other than 1. But just to give you a flavour of what that means, actually, it's still overfitting despite the fact that k is no longer 1. If I set the test data here to be completely different from the training data, now we're going to get an error which is 5. If I look at the plot here, we can't really see it here, but basically it's now genuinely seeing unseen data, so the model is giving a performance which is more realistic in terms of how it would behave when it sees unseen data, and that's 5 and a bit. So now when it saw data that was identical to the training data, it scored about 3. So there's still overfitting going on even when k is 2. I could increase k, and I think that's about 10. I think it probably starts to become a reasonable performance even on previously seen data. But the general point is the k-nearest neighbours algorithm overfits unless you're very careful. Let's just look at nominals. So if I can change the input data by doing this, if I replace the data generation with something that generates nominal values, let's just run it, set it to k equals 2, mixed measures, it will work with this. So we run it, we get now a confusion matrix, because now nominals are both in the label and in the regular attributes. If we look at the nominal data, we're seeing this time nominals everywhere. If I now plot a plot of the actual results, the predictions and the label, and put some jitter on it, we can see negative, negative most of the time it's right, positive, positive most of the time it's right, and sometimes it's wrong in the false positive and false negative cases, which matches this performance vector actually. So you can see that k-nearest neighbour works completely happily with nominal, both labels and attributes actually. So let's sum up with some of the strengths and weaknesses of the k-nearest neighbours approach. As you've seen, it works with both nominal and numerical attributes and labels. It's pretty simple, and it does actually give quite good results. It's quite hungry for memory, and it takes quite a bit of processing time actually if your model's big, because it's obviously had to read the entire model into memory for the training phase. And then when an unseen example is presented to the model, that unseen example must be compared or presented with each training example to determine, let's call it, neighbourliness. And that can get quite slow and obviously hungry. And because it's an instance-based algorithm, it does risk overfitting, as you've seen, but you can, if you know not to use k as 1, you'll be fine. Okay, so let's just run this one more time by, I'll set the various parameters and operators back to be numerical. There we go, and I'll set that to be sum and sum, and let it run. And we can see here's the error on unseen data, and here is essentially a plot between them on the bottom label, prediction on the left here, and here's the raw data.